playing physics.
If anybody wants to go by, I rolled
Oh, did you break something?
I did break something.
Oh, really?
Whose is that?
It's just a
Right.
kombucha. It's just
Yeah.
Water.
evacuated the classroom.
Is that really how you pronounce that, guys?
Kombucha?
Should I put it in the trash? Yeah.
Yeah.
Do we put broken glass in waste baskets?
I broke your kombucha. Oh, shit.
That's okay. Yeah. You gotta wear the special
Okay, show me the
safety
glass.
goggles.
Glass. Careful. Alright.
Hannah knocked it over with her backpack.
It was on the edge and my butt. I didn't know.
Blame it on the edge.
back there.
On the edge floor here now.
Carries around.
Obviously. This week is terrible. What do you think?
Oh, miss.
I'm just happy
Yep.
that it wasn't.
Have a good.
Little alma mater.
That's your the affiliation you belong to. Cool.
Yep. I have a question.
Yes.
About is class starting? Oh, it is 1:30.
Yeah.
It's about the homework. I've been working on it, and I have like some questions about just clarifying variables that I think would probably be beneficial to everybody.
Okay.
Can we go over a few of the things from?
Yes, we can do it in a later part of the class.
Okay.
So I'm gonna do as I mentioned, this is gonna be the last chapter for this class, for the chapter 7. Okay.
What's the next one?
So next will be 10.
Okay.
So it's interesting how traditionally the department separates chapters, because Dr. Young Simon going to teach you guys about solution scattering and dynamics, and which is 8 and 9. So after this, next Thursday, I'm going to start teaching the rubber elasticity. So today's lecture is a very important one. It's basically summarize what we have taught about in the chapter 7. So this is like sort of overview and QA or help session for this particular chapter. Okay. So let's get started. So today we're gonna just do one thing: condense all the knowledge we learned for the past about 4 weeks into one lecture in about 30-40 minutes, and see if we can do that. So what we learned for this chapter, everybody? What's the keywords?
Flory-Huggins
Flory.
free energy and
Wow, you guys really impressed me. That's all I want to talk about today. But yes, so this particular chapter is talk about thermodynamics of polymer in solution. It's very much different with the first chapter we talked about, right? First chapter is nothing about free energy. First chapter is more about chain statistics, how the chain being oriented in 3D space and what the chain model are. So moving into the chapter 7, sometimes I like to talk to students. This is like you're going from a sophomore to junior. All of a sudden, the class getting harder because there's now a lot of abstract concept into it, like entropy, enthalpy, etc. Compared to in the first case, it's just a core. You're trying to understand what the core is, right? But in essence, it's not too bad. Those concepts are very fundamental in terms of thermodynamics. So let's go over what we talked about. So in the beginning of the class, where we started is where we did an overview of what is thermodynamics, right? So at the beginning of class, we started with just a regular theory of dissolving of the polymer, right? We talked about so this chapter is called thermodynamics of polymer solution. where we sort of basically introduce or refresh everybody all these three parameters. And you should be pretty familiar with those three. Delta G, free energy change, delta H, enthalpy change, delta S, entropy change. That's sort of a recap in the first class while we get everybody comfortable with what we are teaching. If everyone remembers what we talked about in the first class. Then we start to talk about very fundamental way. The idea of this chapter is we didn't talk about polymer at the beginning. We just talked about with solvents. So that essentially is called regular theory on mixing. So what does this mean is where we just mixing two of almost identical bead in terms of one is black, one is white. Specifically using this very simple example, we talked about individually what are this, right? What are these? And then what are delta H? And this sort of laid a foundation where the later Flory-Huggins come into play, right? If everybody remember where we first actually talked about, we discussed entropy of mixing. So, where we actually played a little bit with statistic. We discussed what is S will be equals to K. K is Boltzmann constant. Law in number of ways you can place your molecular in the lattice, right? That's what we talked about at the beginning. So this symbol is just called possibility or possible ways to pack solvent into lattice. And if you have more possible ways, you get more entropy into the system. What we moved on from this one is we talked about delta S. After mixing minus where you probably remember we drawed many times this, beautiful lattice before and after, plus another one about 3 by 3 equals to a longer version. And how this is coming into play, right? And in the end, what we indeed understand in terms of delta S of mixing is going to be equal to minus R and this was per mole of
shouldn't we be incorporating temperature into that? Like negative RT?
You will while you consider delta G, because that is coming to delta G is where the temperature term is right there. Okay? So this summarize what would be the entropy difference before and after mixing. And we pretty much know x1 is going to be the volume fraction of the first molecular. X2 is a mole fraction of the second molecule, right?
So
Please?
those are both x's and their mole fractions?
Yeah, so x will be n1 mole divided by n1 plus n2. n1 would be mole of solvent A, and 2 would be mole of solvent B. Okay? So these are just to tell you how much molar fraction of there. If you mix 1 to 1, and we did that calculation in the class, what it would be, half mole of A mixed with half mole B. You can just plug in the number 0.5 here. You can calculate what delta S, right? So what we did now is we understand what the delta S is in the mixing. That's basically the first week of work. We did this calculation. We understand what the entropy difference for the two classes. Then we moved on to look into then we followed a discussion on entropy of mixing. Okay? Because this is a check. Well, we need to check this, then we can get delta G. Okay? So what we did is we figured out delta H is going to be x1, x2. And now we define what is chi is. And there's RT term here. That's a term that is related. So that's a delta H, where again x1 and x2 are the molar ratio. Okay? And chi is where we first time introduced the Flory-Huggins parameter. This is an interaction parameter. And in the last class, we learned what delta chi is, right? There's some physical meaning comes into that. If chi is 0.5, means your material is in a acidic solvent. If chi is larger than 0.5, your material is unfavorable interaction, more dominant, or your material is in bad solvent. And if chi is smaller than 0.5, that's where it's a good solvent. Correct? So that's about one class of lecture. We talked about what the delta H is. But in the class, we actually go through much more detail where we talk about solvent interaction A versus A, B versus B, and A versus B, and how these deconvolute into this chi parameter. Okay? So with all these knowledge, that sort of summarizes the first quarter of this lecture, where we talk about delta G divided by RT will be let's make sure we are correct. And N1 log x1 plus N2 log x2 okay. And this is for system. And some of you have asked what is the difference between system and persistent. So for the persistent and persistent, there's a slightly difference in this term. In one case, we use the RT. The other case, we use KT. So let me write you what it would be the persistent case. Okay, so that will be come into x2 log x2, make it almost a perfect symmetric term. So this is a per lattice site. And the difference between K and R, I'll explain to you what are these differences. There was one question.
In both cases, X is the volume fraction, correct?
No, it's a molar fraction, not the volume, because x1 is N1 divided 1 plus 2. That's how many moles in one material.
So going to this equation.
So they actually would be almost proportional to the volume, because in the assumption is that each solvent has taken the same space. So effectively, they are similarly. Talks about volume fraction. But let me get back to the key point that we constantly switching back Pilates side, persistent, and why we need to do this, and what's the difference. So this comes from this KT and RT term. So what is K? So great answer. How big is K? Right, so it's about 10 to the minus 23 J, right? So that's a Boltzmann constant. How about what is R?
8.314. What did you say? Mole.
So mole inverse and K inverse. So this is called a gas constant. Okay? And the difference for them is just Avogadro constant is about this. Okay? So that's the difference. So if you're talking about Pilates side, you just divide how many moles of your material and you normalize into Pilates side. Or you talk about energy. I like this curve again, or this draw. So you talk about energy per this place inside of one square box. They're proportional. They're just a difference about 6 multiplied 10 to the power of 23. Okay? So up to now, I'm going to erase this part to save some space. Up to now, we understand what is called is regular theory on mixing using the lattice, where we pretty much understand what the entropy contribution, right? That's where the entropy contribution, N1, X2, chi, entropy contribution is here. And something worthwhile to understand is this is always small individual, so promotes the mixing. And this, depending on the term of the chi, that could be promote or depromote. That's where everything we talk about up to now is just we talked about everything for the solvent. And after that, we started to discuss what it was the polymer. Then we comes into the second part where we start to use Flory-Huggins theory. This is the first time we actually introduced this term based on what we learned from the regular theory. And we talked about the difference in each component. And the difference is coming from the conductivity of your polymer, that the entropy contribution, this term will be different. And we defined something slightly different. Phi 1 is now in the Flory-Huggins, it's a volume fraction, okay? So we start to call this will be N1. Phi 1 will be equal to M1 divided by M1, which is how many moles of solvent, how many moles of polymer, and N is degree of polymerization.
So M1 will always be the solvent, M2 will always be polymer, with how these equations are written out?
Yeah, in the theory, that's typically by default, okay?
That's a mole fraction, right? Not a volume fraction?
This is volume fraction,
But M
not the mole.
M is the number of moles.
Yes, but think about this. They have equal volume. Okay, if it's mole fraction, it will not determine how much each individual volume is, right? So 1 mole of solvent, 1 mole of polymer, the molar fraction is still a half. But volume fraction is not, because polymer is much bigger, right? So that's where the phi 1, you need to consider N term here. N is degree of polymerization. or how long your polymer now is, right? So that's where, and phi 2 will be n multiply. Okay? And in the Flory-Huggins theory, we can now make a slightly adjustment. And that's mostly coming from the delta S. So again, this is going to be the lattice side. And if you compare what we talked about in the regular one, the volume fraction, the degree of polymerization is reflected here, where the entropy of mixing now is much smaller from the polymer contribution. Well, the solvent contribution is not changed. This term is basically more similar to that. Okay, so
Are there multiple forms of that equation? Of the
this one?
entropy of mixing? Yeah. In the book, are there different ones where it's like using M or I don't have my book with me, but
Yeah, please ask. There is persistent or lattice side, and the difference is, well, we can also look at this persistent. Okay, persistent means we need to multiply by Na, and the difference is now this will be changed to be R. Okay, and this going to be N1, and this will be N2, and that's the difference.
Okay. And would that, the N, would that be number of moles?
Yes.
So the N1 is the same as the M1, since M1 is number of moles as well.
No, yeah, this actually should be M1.
M1?
Yeah,
Okay.
this is M2. Let me write it out for you so you can have that as per lattice side as well. So that will be minus so this would be the persistent term. Okay? That's how much the total system have. And pick an eye on these has difference by an Na term. Yeah?
So how are you going to get a volume, molar volume from phi 1 if it's all just moles in your units?
So in the theory, we take a most simple and easy way. We assume each lattice of each monomer, or for the polymer, occupy the same space. So unit volume is the same for the polymer and solvent.
Is that a reasonable assumption to make, or are we just doing that to keep things simple?
We just do it to make things simple. The real case, they will be different. But for the sake of, for the Flory to derive this, he need to make some assumptions. That was one of the assumptions that for the polymer, with degree of polymerization n, it will occupy n lattice. And each lattice is the same volume as the solvent. Okay? So coming back to where we talk about the Flory-Huggins, now I have a little bit of space. I can write out delta Hm will be the same. It will not depend on. So that's going to be the per lattice side. Okay? And now I get a challenge where I'm going to write the final equation. I decided to do and talk. So, and that's basically the Flory-Huggins theory, all condensed down to this simple equation. And this equation says, what would be the energy change after you mix a polymer versus solvent? And you see the most magic or the trick happens in the first two class, where while we're trying to understand what delta S and delta H is, we naturally come to the conclusion for the polymer, solvent mixture, it will be this case. Ansley?
If that, the delta G of mixing, but per system, would that just be M1 ln phi 1 plus M2 ln phi 2, M1 phi 2 chi?
Yes.
Okay.
Yes, that's exactly the case. Okay?
So what's the exact relation? Is there an exact relation between phi, M, and Avogadro's number?
No, phi and Avogadro number, there's no relation.
Okay.
It's just a constant. If you look at these two equations, you will see it's these two are slightly different.
Okay.
So coming back to this, we are pretty happy. After half of the class, we actually understand what the delta G is. Or we develop, or we rediscover what a pioneer polymer physicist 50 years ago, he's sitting in his office with a pen and a paper. He found there might be this theory. Okay? Think about you at the great time. And if I was a scientist, I'm going to ask myself, what can I do? I have people who are not going to watch this equation and find the magic sense, right? So this can be applied to the second half of where we moved away from that. Not just look at the mixture, entropy, enthalpy. We applied it to that to a system where we look at the phase diagram. That's a buzzword we learned in the second half of the class. Is a phase diagram. So moving on, we looked at the phase behavior. And specifically, we look at this curve. We draw it again and again where we have the temperature, we have the volume fraction of the phi 1. And we again use the same concept we did here. We didn't directly jump into where we want to use the polymer theory. We started developing the phase diagram using just the solvent-solvent. In this case, we again will use this x1 term, okay? So which is a molar fraction of one component inside it, right? And what we draw is, we draw a generic phase diagram. This is a very generic one, where, what is this curve? What's the name? Binodal or spinodal? This is binodal, right? And in the center one, you got a spinodal. So if you're hesitating, you might want to have this keep in mind, right? And where we talk about phase diagram is basically a diagram. You can look at your material, where it mixes or not. And there is one phase, or mixed phase. In the bottom, this is two-phase, or non-mixed phase, right? And this is the metastable phase, where it's not so stable. It will form spinodal decomposition if you have a large fluctuation. And we're sort of cheating because we directly talk about conclusion. There's a lot of things we haven't discussed is how do we get this curve? And that's directly coming from this equation, or this very important free energy equation. We have defined a few key things on this plot, because if you know a few key points, you can find this curve. And a few key points are, what's the condition for spinodal? What's the critical point, right? Like then you say, oh, what is spinodal point? All right? So we basically define what is binodal. And this actually use a different plot, and you will see it many times where instead of plot temperature, versus volume fraction, we plot delta G. In other words, you look at this equation, that's your y, that's your x. This is also related to x, this is also related to x. So this looks like a little bit complicated, but in essential, it's y equals to x function. In generic case, we can draw something like this. And how we determine the binoodal is where the tangent of these two curves. Okay? We talked about that. And we also talked about define spinodal. Where we look at, we know it's second derivative of delta G equals to 0 is the spinodal point. Or when the slope is start to converting this curve from concave up to concave down, right? We know that's the definition of spinodal curve. We talked about this very important point, and there's one more thing that one student mentioned is critical point. We also talked about in the class, critical point is third derivative of delta G derived by n1 equal to 0. So using in a nutshell, what we had is we use what we learned for the first two class. We can plot this out and use that. We can get the phase diagram for our material. Okay? That's the whole concept about chapter 7. The chapter 7 is trying to help the scientists, if they know entropy, enthalpy, then they can use that to understand delta G or free energy difference. Use free energy difference, they can use that to construct a phase diagram for any material. And we start with something relatively simple. And if the critical point is on the top, this is actually UCST, or upper critical point phase diagram. Okay, the U means upper. And there will be another case where you will have something look like this. So this will be called LCST because it's lower point in the curve. This type of critical point at the bottom of the curve, which means if you heat the temperature up, your system will from mixed phase into demixed phase. In this case, if you heat up, your system will come from two phase into mixed phase. Okay, they both exist. Well, we are sort of 60% over the class we taught in the past months. At this point, we kind of have some idea how you would get the phase diagram of the material. Please?
What materials have a lower and upper, so like both graphs are on the same graph?
The textbook gave an example. It's actually not easy to predict. So it's basically most of the time people would measure that. And I believe in the textbook they talked about polystyrene in one organic solvent where they have both upper and lower critical point in one material. Which means if your material at very low temperature, it will phase separate. If you heat up, it will dissolve. Keep heating, it will phase separate again. Okay? Then we will, up to now, we only talk about the solvent case. Then we did one more step is we replicated what we did here. We now applied the Flory-Huggins theory to understand the phase diagram. And after applying, the only difference you will get is now the phase diagram is no longer symmetric, whereas this is a 0.5, so you have a symmetric if you mix in solvent. So if it's a polymer solvent, this is what you would get in terms of phase diagram. Okay? So you're pretty much, all the data point is screwed into one side, and that's coming from the Flory-Huggins theory. If you do derivative of this, you will realize this n will play a role while you're constructing the phase diagram. And this is reflected into xc. First, it's a phi 2c. So this is where the phi 2 at the critical point. And this phi 2, or where it corresponds to the tip of the phase diagram, tell you this is equal to 1 divided by root of n. What does this mean? If you have a polymer had degree of polymerization of 100, your phase diagram is shifted from originally it's at 0.5 to 1 divided by root 100, that will be 0.1, right? So this would be the case, which means your polymer has a strong influence in the entropy and reflected in the phase diagram. If you put 0.1% of polymer, they are less likely to dissolve in this case. Okay? Up to now, we are pretty much understand 99% of what we talk about in the phase thermodynamics of the polymer solution. We started from entropy, enthalpy. We moved on to understand what delta G is. From delta G, we understand two phase diagram. In one phase diagram, this is solvent, solvent. This is a solvent polymer. And at the point, I think we're all set, right? Then we realized we have one more problem we haven't talked too much. That is chi. And that's why in the last 1/4 of the class, we talked about what is chi is. We discussed for the last two lectures, we discussed what is Flory-Huggins parameter chi. We basically in the last very part, we talked about definition of chi and what this very important parameter in our class is. It sounds very simple. It's called Flory-Huggins, but this parameter pretty much determines if your interaction is favorable or non-favorable. Okay? So I'll jump into the conclusion. Chi is interaction parameter. So we pretty much learned 3 scenarios for good solvent, and zeta solvent, and bad solvent, right? We discussed all 3 cases, and we realized that chi is actually uses 0.5 as a benchmark. So if we have chi equals to 1/2, you are in the zeta solvent. And how about good solvent? Less than 0.5 and larger than 0.5. Very good, everyone. You will get a bonus point. Except the Nathan. And we also have a second way we talk about in the class, how we can define what is chi is, right? There's a second way we can use imperial equations to look at what is chi. Okay, so V1 is unit volume per lattice. You can think about this as a constant. Don't worry too about that. RT again R is a gas constant. T is a temperature. And what is important is this delta 1 and delta 2, and delta value is for a given system. And I think I mentioned that you can find a textbook or a polymer handbook. Just look at what the solubility parameter is. So if you know what is this guy, what is that guy, you can plug in and get what the chi value is. Then apparently you know already quite a lot for your phase diagram. I believe that's more or less what we almost to talk about, except the one thing we haven't discussed. What is it? Yes, that's osmotic pressure. And why that come into play, all these lattice theory, Flory-Huggins. The reason people wrote textbook into that is just because, as you mentioned, that's related to the solvent quality. And it's very direct way you can check the solvent quality, right? What is that parameter called? In the last part, we discussed and I purposely moved it into the last part of the lecture because I feel the flow is better. We talk everything about Flory-Huggins theory, then phase diagram, then lastly to this parameter. And in this theory, we basically learn your osmotic pressure divided by RT will be following this equation. And this is osmotic pressure, gas constant, temperature, equals to concentration of your polymer divided by number average molecular weight. B is called second virial coefficient, and B3 is third virial coefficient. Most of textbook actually omit this part because it's already small enough. Okay, in a dilute solution, C is very tiny, so C power of 3 times is very tiny. And we learned, and we also did it in the homework, C divided by RT will be a direct way, can tell you what is number average molecular weight, as in here, where B corresponding to 3 solvent quality. And this is bad solvent, this is theta solvent, and this is good solvent again. And correct?
Which one is good solvent?
B larger than 0. Okay? And we also know this is a partial derivative related to, it's somehow related to delta G, right? So we also did one more task before in this chapter is we actually derived a correlation between what is B and chi is. I don't have enough space, so this actually goes to here. So that's a connection between B and the chi. It's basically B equals to okay. That's where these parameter and this parameter in the end talks about the very similar thing. Okay? Pretty clear, everyone? That's how osmotic pressure and how this thing come into play in the chapter 7. Yeah?
The equation you just wrote, is it plus V1 or is it just multiplied? 1/2
What is
chi.
equal? B equals to, you talk about here.
The one above it.
Oh, this is plus, and there is multiply this term.
Okay.
I don't have space, so this should be, behind this. Okay. That's coming from, again, Flory-Huggins, how you can understand osmotic pressure linked to chi. Ansley, please.
Sorry, I have so many questions.
Take your time. Yeah.
From when we started out doing like our phase diagrams and everything, and I believe it was still while we were doing solvent.
Yeah.
One of the free energy equations is where we have N1 ln x1 plus N2 ln x2 plus N1 x2 chi was one of the equations we used.
Yeah.
What is that? Is that interchangeable just with the volume fractions then?
Very good question. So, well, in the solvent cases where we don't need to worry about volume fraction because molar fraction is equal to volume fraction. They're the same.
In solvent.
Right, because solvent occupy one lattice.
Right.
Solvent B also occupy one lattice. If you know the molar fraction, you know the volume fraction.
Okay.
But it's different in the polymer case. Well, that's why we use the phi 1. Okay?
Mm-hmm.
And you can check back. If that still confuses you, feel free to ask me some of these questions. And in the end, what we learned, the broader picture, we walked us through one more time. We go from the free energy. We understand entropy and enthalpy contribution. We started with the solvent system where it's very easy to understand. Like there we cut the confusion about the volume solvent. That's why we get the first with the contribution from connectivity, right? And the key is, again, I want to emphasize, Flory-Huggins emphasized the contribution from connectivity. And that end term or degree of permutation is very important. With that, we go ahead, derived or use the Flory-Huggins or lattice theory to understand the phase diagram and understand what the phase diagram means in terms of how you can predict if you mix in two things together, will they mix or not mix, or they will then phase separate.
M there is your number average molecular weight, right?
Yeah.
Okay.
Yeah, that's number average molecular weight. And I didn't go through the detail why this is a case contribution. Then that's contributed where this is number average molecular weight. Mm-hmm. Well, in the light scattering, it's weighted average molecular weight. That's slightly different. Okay. Very good catch.
The V1 n squared over m squared, you only use that if you aren't assuming that they take up the same molar volume?
I didn't get your question. Can you ask it again?
The term that you incorporated there,
in this?
n squared over m squared. Yeah,
right.
You use that to adjust for different sizes, like your molar volume, correct?
V1 or molar volume, it's basically just a general term. It's unit volume solvent or per the lattice side. Mm-hmm. You can think about its abstract term. It just happens to be the same volume one solvent occupies. In the reality, some solvent occupies a bit more, some occupy a little bit less. That's one of the limitations for this Flory-Huggins theory.
So we can use that same term and incorporate it into our normal pi over CRT equation. We can incorporate that into the BC term as well.
Right. You can do that.
Okay.
You can do that. So this is just trying to connect what is chi and B is. Mm-hmm. That directly tell you what they are and how they are correlated. That's why the rationale behind this. You have two metrics you can evaluate your solvent quantity. Okay. Either use chi or B. They both tell you if your solvent quality is good or not. So with that, not too bad. About 50 minutes we covered what we talked about the past months, and we come through what we talked about thermodynamics and phase diagram. We can take a break, then come back to go through some of the questions in the homework. If there's anything I need to clarify, we can do it after 5 minutes. Okay.